We're given f of x comma y equals xy, and now to determine the directional derivative of the function in the direction of the vector with components -2, 6, and at the point 1, -3. Let's begin by looking at this graphically. So here we see the graph of the surface, and we're asked to find the value of the directional derivative at the point 1, -3, which should be this red point in the xy plane. To find the corresponding point on the surface, we need to find the z-coordinate by substituting 1 for x and -3 for y into our function. And that would give us this corresponding point here on the surface. And again, we're asked to find the value of the directional derivative from this point in the direction of the vector with components -2, 6, which should be this red vector here. So if we're on the surface at this point and move in the direction of this red vector, the value of the directional derivative would be the slope of this blue tangent line to the surface at this point in the direction of the given vector. And notice how if we're on the surface, we move in the direction of the red vector, we would be going uphill, and therefore the value of the directional derivative is going to be positive. So hopefully this illustration helps explain what the value of the directional derivative actually means. Now let's go back to our work. For a quick review, if we're given a function f of x comma y which is differentiable, the directional derivative of the function f in the direction of the unit vector is given by the partial derivative of f with respect to x evaluated at the point x comma y times cosine theta plus the partial derivative with respect to y evaluated at the point x comma y times sine theta. So to find the value of our directional derivative, we'll need to find the partial derivatives, then evaluate those partials at the point 1, -3, and we'll also have to find the unit vector in the direction of the given vector. So we're given f of x comma y equals xy. Let's first find the partial derivative with respect to x. So we'll differentiate with respect to x, treating y as a constant. So the derivative of xy with respect to x would just be y, again because we're treating y as a constant, and the derivative of x with respect to x is 1. Now we need to evaluate this at the point 1, -3, which is just going to be the value of the y-coordinate, which is -3. And now we'll find the partial derivative with respect to y. So we differentiate with respect to y, treating x as a constant. So the derivative of xy with respect to y would just be x. We evaluate this at the point 1, -3, which would just be the value of the x-coordinate, which is 1. And now we're given the directional vector, let's call it vector v, has components -2, 6. We need the unit vector in the same direction, which should be equal to vector v, the given vector, divided by the magnitude of vector v. So we'd have -2, 6 divided by the square root of -2 squared plus 6 squared. So we have the given vector divided by, this is going to be the square root of 4 plus 36 or the square root of 40, which does simplify because 40 is equal to 4 times 10, and the square root of 4 is equal to 2. So let's rewrite this as -2 divided by 2 square root 10, comma 6 divided by 2 square root 10. And now we'll go ahead and simplify these components. Remember, because this is a unit vector, the x and y components are going to give us the value of cosine theta and sine theta. So we know the unit vector in the direction of the given vector would have an x component of, this would be -1 divided by square root 10, and a y component of 3 divided by square root 10, which again is equal to cosine theta, comma sine theta. So now we have all the information we need in order to find the value of the directional derivative at the point 1, 3 in the direction of the vector with components -2, 6. We know the value of the partial derivative with respect to x at the given point equals -3. We know the value of the partial derivative with respect to y at the point is +1. And we also know cosine theta equals -1 divided by square root 10, and sine theta is equal to 3 divided by square root 10. So let's go ahead and find the value of the directional derivative on the next slide. So the directional derivative of f at the point 1 comma negative 3 is going to be equal to the partial with respect to x at the given point is equal to negative 3 times cosine theta, which equals negative 1 divided by square root 10, plus the partial with respect to y at the given point has a value of 1 times sine theta, which equals 3 divided by square root 10. So we have 3 divided by square root 10 plus 3 divided by square root 10, which equals 6 divided by square root 10. So this would be the exact value of the slope of the tangent line at the given point in the direction of the given vector. Let's also get a decimal approximation for this. We would have 6 divided by square root 10, which to 4 decimal places would be approximately 1.8974. And let's go back to our graph one more time. Again, we just found the slope of this blue tangent line to the surface from this point in the direction of this red vector. Notice how if we're on the surface, walking in the direction of this red vector, we would be walking uphill along this blue tangent line, and again, that's why the value of the directional derivative is positive. I hope you found this helpful.